All right. Yeah, so we're going to go now into support vector machines, which I guess is section 36 now. So this is kind of like, let's hear, next time I think it's 37, which is PCA. So I think that's right. Yeah, I think that's right. So this is kind of like our last like supervised learning for a while. And then we'll go into unsupervised learning for next week. Okay, but starting with PCA. So that'll be fun. All right. So let me go ahead and share my screen and support vector machines. And I double checked how my code was there, so I think we're all good today. Let's see here. Okay, cool. So we're gonna start off with support vector machines. Oops, I lost you guys. Where do you guys go? Come on, Windows. What? Sorry, I'm like scrolling. It like keeps disappearing off to the left versus the right. That was weird. Okay. So now I can see your guys' faces, your reactions when I tell you about support vector machines. So it's another supervised learning classification. Support vector machines, I thought this short was great. I think I saw you guys on Halloween. I sent you guys my costume for neural networks, and it killed me. Another cohort, I said like, oh, I was dressed up as a neural network, you know? And then I said like, oh, it'd be fun to be like a black box model. Like I think that would have been also interesting. Like it'd be like a big black box or something like that. And it said like, oh, I thought you would have dressed up as a support vector machine. And I'm like, like completely missed opportunity. I was so frustrated at myself. Like I said, I should have been a support vector machine, but next year, I guess. Which is funny though, because one of the other data science curriculum team members dressed up as a random forest. His name is Forrest, and I thought that was just great. I've seen random forest before, but I was like, oh, that's a good play on words. Like only if I had a name that would, you know, be similar to another machine learning algorithm, then I could have also reached that level of, you know, anyway. So anyway, support vector.
You just have to make your own.
Yeah. Yeah. It kills me still. I should have been a vector machine. Anyway, so support vector machines is another supervised learning technique. And basically what's kind of cool about support vector machines is that we actually will sacrifice accuracy to get better boundaries. So support vector machines are a really useful tool to use to basically trying to figure out these nice boundaries, where especially where it's like the boundaries are a little more soft, where there's a little crossover and stuff. Support vector machines do a pretty good job of trying to figure out where that boundary should go. So it's a really great and useful tool. I believe it was like really started used like in the 90s. And it was kind of like a really like big part, and it's still really useful today. So kind of quick question. When would it be better to have a defined boundary over accuracy? And you all know what I'm talking about when I say boundary, right? Like a line that would split the classes together. So when would it be better to have like a better defined boundary than over the accuracy?
Well, I don't know if this is a wrong answer because I'm not caught up yet, but maybe because you don't want to like overfit. So if your boundary is like super well defined, like you can, I mean, or your defined boundary makes you maybe less accurate, but you wouldn't be overfitting.
Yeah, I think you actually said that really well. Is that a lot of times, like you can see like this example, usually our examples are really clear. Like this is like, oh, clearly if I make a good boundary, I'll still have good accuracy. But one example, right, if I were to imagine drawing a little bit of extra data points, like let's say I have some extra green points over here, where I had like a green point that was right over here, green point right over here, and let's say like a green point that was like over here, right? Is that this is like this boundary now like does make mistakes. It's like it's making some mistakes where green's on the bottom and red's on the top, right? So you can kind of see is that these 2 points are incorrectly being identified, right? But if I did something where I sacrificed, I try to get higher accuracy for a better boundary, I would say this is a better boundary right here, is that I might have done something that's closer to overfitting, where I'd go like this, where in reality, it doesn't really make sense. These are just turned out to be outliers where the real boundary really should be about right here. Maybe, you know, like it could be adjusted some, but it might be better to actually have this boundary versus like looking at these outliers. So we kind of like can help us prevent overfitting in this case. Cool. I'll show another example too of like where this looks like of when it performs well. So this is where kind of the motivation of support vector machines come from. So we're going to look at these two different lines here, and we're going to say like which one is better. So I just plot out these random data points. Actually, it's not random. It's from the iris data set. I love the iris data set because it's nice and small and easy to manage. We'll see this again and again. But we can see here the iris data set, and I made two different lines here. I drew them out myself. They're not anything special. And I want to ask you, which of the lines would you say is the better line? And note that they both separate the yellow and the purple from each other. But which would you say is the better line?
I like the red one better.
Okay, this middle one down here, right?
Yeah.
And I saw some nods. And can you express like what, like, I mean, maybe some intuition, like why this one feels better?
Well, okay, I know that the technical reason that it's better is because it has a bigger margin on either side. But that just means that if we got some of our validation data in there or future unknown data, and maybe some of those yellows and purples creep a little closer in, you want to have that, you want to put the line in the spot where you've got the biggest margin, so that you've got a better chance of any of those creepy ones actually falling on the right side, the correct side.
Yeah, right. There's a lot like less room, even though they technically are accurate. You can see is that this is not going, like if there's like one part in the validation set like comes over right here, or one over on the purple on this side right here, or like you can imagine like the purple tends to be on this side over on this maybe pop over on this side, this blue line in the diagonal is not going to do as well, right? What's interesting though is that note from the classification that we've done, these both have the same accuracy. Basically the model doesn't really know any real big difference between the two of these things. There's some ways we can kind of enhance this a little bit. We can talk about like the mean squared error, but in this way, excuse me, for classification, there's not like a real like way for us to like evaluate it, or at least we haven't really talked about ways we evaluate this. So this is where support vector machines really come in. So the idea here is like there's something oh, sorry, go ahead.
So it has the same accuracy because none of the points within each color are crossing over the line.
That's right, yeah.
Okay.
Yeah, there's the same precision, same recall, same accuracy. Yeah.
Okay.
Yeah. And so this is where we basically come down to the fact that support vector machines can kind of encompass this extra information about like, this kind of like what Jenny's mentioned, the margin, which we'll talk about in a second. But again, basically it comes down to accuracy. Accuracy isn't everything. So we could say like the same lines are the same accuracy, but there's definitely more to it. And the big thing about it is it's not just about how accurate it is, but also the boundaries. So we can actually determine this before we even look at the validation data, right? As you guys can kind of intuitively understand like what these lines should look like. So the real question is like, how do we define this better boundary, right? So the way we can think about this, like Jenny said, is this margin. Basically, how much like kind of like a little extra space between these two, like what's it called? These two data sets look like. And so this is what we call this margin here. And the way you can also show it, and I'm going to plot out these margins here, so big margins and smaller margins, is that you can take this blue line that we had from the original, and you can see like these two yellows that are opposite of each other, and then these red lines right here. You can say these are the margins. And I think actually it's the hands-on machine learning book mentions about this, calling it like streets. It's like the biggest street you can fit between these two data sets. And essentially that's what the margin is. Like we want to make as big of a street as possible to fit between the two. And note that this will kind of play into a kind of back and forth because we want it to be accurate, right? Obviously, if we have big margins, but it's not accurate, not very good, right? But we also want to we want to also make sure it's not so accurate that we sacrifice a better boundary. Basically, we want to make those margins as big as possible. So we kind of have this way to kind of incorporate those two competing ideas with each other. So the question is like, how do we do this, right? So the way we can do this, essentially we have one is how many are misclassified, essentially what accuracy is, right? Saying, well, how many mistakes did we make by making this boundary, this blue line in this middle right here? And then we say how many are in a bad boundary. So basically how many points are within this margin? They're not supposed to be there, or they're, what's it called? They're within this margin, which is going to kind of be part of this error. So essentially what happens, and remember, we're going to use error essentially to judge how well our model's performing. So we can do things like gradient descent and stuff like that, or approach a better and better model, right? So this error total is going to be something like the error of the classification, kind of like what we've seen before, then plus the error of the margin. So some margin error. So like how good of a margin was it, okay? So the big part, we know how to find this part. This is pretty easy, saying how many mistakes did we make, right? Straightforward. But this one's a little less clear. We haven't talked about saying how would you define where the mistakes are, or what's a bigger mistake in the margin. Okay, so this is where I'm going to go a little bit kind of going back to like a linear model. And so one thing to kind of note is that we can always create these like lines where you can think like planes or hyperplanes with like this kind of form. And note that this W here is going to be a matrix and X is going to be a vector. So if I were to write this in its full glory over here, its full form, this would look something like W1 times X1 plus W2 times X2. And then we have like 3 dimensions, plus W3 times X3 plus B equals 0. Okay, and then this could have more, right? It could have more W's, but usually we abbreviate it with this matrix notation and this vector notation, okay? Since they'll basically be multiplied out to do the same thing. So what's kind of cool is that we can actually write this like, okay, this is like the base vector, or the base line right here. This is the border. Does Wx plus B equals 0? So we can create this line, and note that this has to be a line. Note that there's no y in here because we're essentially using x and x1 and x2. So that's really what we're talking about in this case, because in classification, there isn't a y target, right? There isn't like a y-axis in the same way that we would do regression, which is the target. So we can just say, okay, x1, x2, x3, x4, and so on. So this will actually create a vertical, well, not vertical, sorry. This will create a line or a hyperplane, right? Depending what dimension you're talking about. And so that's what this will be defined. And then we can basically create more linear lines or linear hyperplanes, right? And by saying, okay, we increase it by 1 or we can decrease it by 1. And so, for example, this guy right here would essentially be, this is my line right here, Wx plus B. And then the yellow lines would be something like Wx plus B equals 1. And then this red line would be Wx plus B equals 2. And then you'd have the opposite, Wx plus B equals -1, and Wx plus B equals -2. Okay, so that's how essentially how we would define these extra lines kind of going outward, and we can expand it out as far as we want. You can almost imagine like a gradient, kind of like starting from 0 kind of, and then going out from like positive infinity and negative infinity. Does that make sense? Okay, so that's kind of like how we can define this part. So we can do classifications, pretty straightforward. We basically start from, classification, we just say, we count from this middle part and say, okay, how many errors does it make? If we have a purple on this right side, we have, a mistake there, and we can count that as our normal errors, classically go through. Our margin error, which is kind of the new part here, is we can first of all say, okay, we can define this margin. So this margin is defined as m equals 2 divided by the norm of w. So know that the norm here is going to be the w, basically w1 squared plus w2 squared plus w3 squared plus w4 squared, all of those summed up together, square root. So that's kind of like finding the norm of this w. But what's kind of cool is like, okay, we can define the error then. It's just saying, all right, taking the norm of w here and squaring that, and just saying, okay, that's going to be the error term. And that's just simply going to be w1, the norm of w1, plus norm of w2, plus norm of w3, and so on and so forth. So the idea here is that if we have very, very large margins, we have low errors. If we have a very big margin, right? I'm sorry, if we have a low margin, we have big errors. So they're kind of inverse of each other. So it basically encourages, like, remember, this error is the thing that we want to minimize. So we'll want to have larger margins, okay? Turns out what's kind of cool, because we're doing regularization here with this r squared, turns out we're actually doing L2 regularization. So if you remember back to when we did, like, for linear regression, like how to regularize that, that's actually the same form of what's going on here, okay? So essentially, that's what's kind of cool, is that by increasing our margin, we're actually regularizing, which means what happens when we perform regularization on a model? Does it overfit or underfit? Or tend to overfit or underfit?
It's to help you not overfit, right? Like if
That's
you're
right.
overfitting, you want to regularize to kind of smash it a little bit.
Exactly. Yeah. So this is basically the reason why we can use this margin, to basically prevent overfitting, right? Because it's the same thing as L2 regularization. Okay. So what's kind of cool then is that we can define these. I'm going to think if I actually put this in here. Okay. So this error here will basically define on this margin. And you can kind of think of it as a sense of saying, if we count of, if we don't count, like in classification, I'm going to kind of draw a little bit with the yellow here. In classification, we just care if it's on the left or the right side, right? That's separated. For support vector machines, essentially what we'll do is we'll count like kind of on a little bit closer to the normal. So let's say we have a yellow point that's like, this might be hard to see, but we'll see how it forms, like right here. And let's say like right here. Okay, so what we do, we essentially start off, instead of having from this boundary, we actually cut over here and say, okay, how many were incorrectly identified on this right side here? And so instead of saying, okay, like how many yellow were off from the side, we actually start from over on this side right here. And we basically increase this error. So basically we're counting the ones that are in this margin. And if they're more in that margin, they'll count more against us. And essentially that's what this error is incorporating in here. Okay, so it's kind of like a mix between the classification and like how big this error is coming through. So we can combine that together. I won't go through the whole math, like how you would write this, because there's resources. Now I think even the curriculum actually goes to this, but essentially you can combine these two together to say how you can count these together. Okay, but the main idea is that we can say there's a classification error, how well it performs to classify, and the margin error. And then we combine those together into this guy right here. And all we have to do now is gradient descent to minimize this error. Okay, makes sense? Cool. Any questions on kind of this margin error or classification error? Okay, cool. So one thing I'll note is that there's something called the hyperparameter C. So C here is a way for us to adjust that dial to whether to increase, what's it called? Whether to care more about the classification or care more about the margin. So you can imagine for certain situations, you know, you want to adjust the C. And know that we call it a hyperparameter. Have we talked about hyperparameters yet, really? Yeah, okay, I see a little bit nod. Just to re-emphasize, because we'll talk about this a lot, a hyperparameter is a parameter that doesn't matter so much about the actual model. It's more about how the model will learn. So that's a key kind of distinction. And that's why we call it hyperparameter. It's because it's like one step removed from actually creating the model, right? So essentially it's like, okay, this hyperparameter will say, okay, if we increase C, it's going to tend to, it's going to tend to either care about classification or care more about the margins. So if we adjust C in a certain way, it will basically make the margins smaller or bigger, okay? And that will basically be reliant on overfitting or underfitting. So note that this basically is classically written as our error total is equal to C times the error classification plus the error margin. Okay. So what happens if C is very, very large? What errors would we care more about?
The classification.
Yeah, right. So that error is going to basically, that classification error is going to be really enhanced. Remember, gradient descent wants to squish it down as far as possible. So if it can basically decrease its error classification more, it can decrease the overall error much faster than maybe decreasing the error margin. Okay. So yeah, so basically, big C will give us a smaller C. You see, I corrected this. Shouldn't give a smaller C, should give us a smaller error. Or I don't even know what I was trying to write here. See, I fixed this before. Okay. Oh well. But yeah, it would basically, if you get larger C, it would care more about the classification. Okay. So it would give us smaller margins. All right. Cool. So that is hyperparameter C. Note that in sklearns, we'll show you a little bit of that, but sklearn basically you can set this hyperparameter. Cool. So now I'll lead us into the kernel trick. So kernel trick is a really fun way to apply the support vector. Kind of an interesting thing that we can use support vector machines. Kernel trick isn't just for support vector machines, but it's the most obvious, I think, with support vector machines. So the idea here is like when a simple model just isn't good enough, we can extend it to higher dimensions, which seems like it's like, okay, like why would we want to make it more complicated, like in this case? But it turns out this actually has a huge advantage to a lot of things. So kind of discussing a little bit about higher dimensions, like what this looks like. Actually, I'm going to draw a little figure here. So imagine we have a little example here. We have one-dimensional data, okay? And we have, I'm going to use red. That looks closer to black, but that's okay. And then we have something like, let's say blue. Okay, and I say, okay, draw a line a straight line through this, draw one straight line to separate these points. Can you do it? Yeah, no, right. We don't have to go through like whole preschool kind of feels like, well, duh, no, we can't. Like no matter what line we do, we're always going to have incorrect, but moving over. However, imagine if we could like, well, what if we like, I don't know, kind of cheat this a little bit. So imagine this is like, you know, -1, this is 0, and this is 1, right? What we could do is like, well, let's just go ahead like square this and say, okay, we have this new feature. Instead of just x here, we have like x squared, right? And say, okay, well, that means we can say square this part. Well, that means this is going to raise up to 1, right? This will be 0, and this will also be 1. So this will look then like, that's a different color, but that's close enough. It'll look like this, and then that blue one will stay the same. You can imagine these don't exist anymore, right? And then say, okay, well, if we have this, then we can draw a simple straight line right through both of them, like this. And now we can separate this. So essentially what we did here is that by having this extra power, basically by using another dimension, right, we made it more complicated, we actually are able to separate this. And this actually comes out something interesting with increasing dimensions is that as we increase in dimensions, there tends to be more space between points and stuff. So you're actually more likely to be linearly separable when you go into higher dimensions. So it's kind of a nice kind of feature that we can do. Now, one thing we could have done too, so we can have this part, right? It's like, okay, we can define this like, you know, y equals, or in this case, like x squared is equal to, let's say 0.5. Okay. So what's interesting is like, well, what we could have done then is say, well, instead of having x squared equals 0.5, what if we just said like x equals the square root of 0.5? And note that when I say square root, I can do plus or minus. Well, that would basically put in 2 lines right here, and that would have been linearly separable, right? So it's kind of cool is that you can actually go either way. You can either say, you can raise these up into higher powers, or you can treat your line essentially that you would separate it into a lower part. And that's the kernel trick, is that these are actually equivalent to each other. So we'll see a little bit of what this looks like in a second, but I'm just gonna show that example. The main thing is that the kernel trick allows us is we can take a line and basically, or like any information, and extend it to a higher dimension, right? And essentially we're making it a higher degree polynomial. So one thing we can do is like we start off something like 2D data. So we start off something like x comma y, right? So we just like x and y, or x1 and x2. And say, okay, what's all the possible ways we can combine it? Well, we can have x and y. We can maybe raise it to x squared. We can do x times y. We can do y squared. So now we have a lot more things to play around with. And so what's cool is that we can actually take this, take the data points and say, all right, let's plot instead of 2D data for x and y, let's plot it into, in this case, 5-dimensional data, saying, okay, there's x feature, there's a y feature, there's an x squared feature, there's an xy feature. Obviously, I can't draw in like 3 or I can't draw in 4 and 5 dimensions, but the idea is that we're basically putting these data points into a larger dimensional space. And then we can say, okay, once we have these data points, let's draw a single hyperplane that cuts through these points, separates them because it's likely to happen. And we can take that hyperspace and then drop it down into something easier to do. And it turns out we can either map it like this, where we extend it out into higher dimensions, or we can basically start off with the actual function being adjusted into a nonlinear space. And it turns out those are equivalent to each other. Turns out too is that this, you can see already, is kind of similar to like polynomial regression, right? So we remember doing that. It's kind of similar to this, but what's kind of cool with the kernel trick is that we don't have to go into the higher dimensional first. We can actually do it directly with something called the kernel. And the kernel basically is this thing that allows us to split up the different groups. So it's a new way to kind of like draw the new boundary around there to split up into different groups. So that's what we call it kernel. So one thing we tend to do is something like a polynomial kernel for something like for support vector machines. So it turns out to be much more efficient. Okay. Yeah, okay. So that's kind of like the idea of this kernel trick. Does that kind of make sense? Is that we can raise these into higher dimensions and then split it up? Does that make sense? And then the hard part to kind of realize is that you can actually just start from the beginning with a better kernel, essentially, that would be equivalent to putting into higher powers and then separating them out. Okay. So for support vector machines, you can start off with a linear kernel, which is like what we classically would do. But you can actually start with like higher kernels, like for example, polynomial. But a classic one is the radial basis function, the RBF. So this is basically a way for us to kind of split it up. And the RBF is a really convenient way to raise things, essentially, basically create a kernel without ever having to raise things into higher dimensions. But it's kind of useful to kind of see what this looks like. So I have, it's about 20 minutes. Okay. So I'll see how this goes, because I do have, you can see all these little lines right here. But basically I'm going to show this little motivation, like how this RBF works. So remember how we kind of like raise those guys into like a parabola, right, from that original one. We're going to do something similar, but instead of using a parabola, we're going to use something called a radial basis function, a radial basis function. And so one thing I'm going to skip over is the actual equation for this. The equation does like, it's like e to the power of like, I think it's like negative x or something like that. Essentially, I think it looks very close to Gaussian. It's not quite Gaussian, but it's kind of similar to that form. And so the idea here is that we can actually center each RBF, right, this function, at a certain point. And what will happen, basically, it will be maximum at that centered point and then kind of trail off into infinity off to the side. So it's kind of cool is that we can say, okay, we have a red point and a blue point, right? So a blue point right here, red point right here. And these dashed lines here represent this radial basis function in 2 dimensions. So the idea here is like we would raise this blue guy right here. We'd say, okay, let's go ahead and raise you up. Oops, let's draw, there we go. We'd raise this guy up to here, so the point lives over here. And then this red point, I probably should have drawn this differently, but we can actually say, okay, every time it's red, just times it by negative. And so it looked like the inverse looks like this. And drop this guy down to here. And what's nice, then we can definitely draw a line straight through here. Okay, and what's kind of cool about this is that it turns out we can combine these parts. So right now we have like a blue function and a red function for these 2 points. You can do this for like multiple points. If you had 5, 6, 100, 1,000 points, right? You can do this all the way through. But then we can actually combine it into one large function, right? And this one large function will become that kernel itself. So I'll show you what that looks like now. So you can see here we create this one function, and essentially, if you remember back when we did KDEs, and I showed you guys the little Gaussian, and they kind of add them up together. That's kind of what's going on here. They're being added up together. In this case, I probably should have made it negative, but you can imagine this overall function, if I did the negative side, would look something like, oops, get my drawing tool, there we go. It would look something along like this. Okay, and so this creates this one large function. And note that I just have 2 points here, but what we can do is actually have it with, oops, we can have it with even more points going forward. So you can see how we have 2 points here and they kind of create together to create this large function. And note that I should really have this negative, so it drops down to this point right here. And so we can say, okay, like what if we had 5 different points? So what this would look like, since we actually know how to draw each of these radial basis functions for each point, basically it's like, okay, like we have it centered right here. We say, okay, blue is gonna look like this. It kind of spreads out this way. We could have blue go something like this. And note that I'm kind of like drawing out, but this would be like a strict mathematical function. And then red would have also radial basis function, but it would be negative in this case. And you can see here, we'd have something similar for these 2 reds over here. So again, not the best drawings, but I think you guys get the point of like how these kind of combine. So you can draw these parts out here and say, okay, let's combine them together. And what that would look like would look something like this, where we have it kind of increasing it and bump up, and then you can kind of see like it kind of goes downwards. And then it would have something like maybe 2 extra bumps right here. And so this would create this one function because you can combine those 5 different radial basis functions, combine them together into one large function, okay? And what's nice, then we can actually separate these out by, you can imagine separating them out by moving them up in this direction and separating them through. But what's cool is that because we're doing the kernel trick, we can just say, hey, let's just design this thing and translate this function onto the lower dimension, right? So you actually be able to create essentially where those lines will kind of split up and stuff like that. And so that actually will make it easier, and it's actually more efficient than us trying to move these lines through here and then find the best place to split it. We can actually design this radial basis function and just say, well, how would we project this downward? That turns out to be much more computationally efficient than us trying to raise them up into a higher power, look at where the best way to split it is, which is basically polynomial regression, right? And then go from there. So that is the basic idea. Actually, I have one last thing here. I think I just showed another example. Same idea here with just more points. Do you guys have any questions about this? About like kind of how these little radial basis functions are formed? How are we feeling on this? Thumbs up, sideways, thumbs down. It is kind of strange, right? I don't think it's like super intuitive by itself, right? But the main idea here is that we can basically make these little tiny functions by just knowing where the points exist on the plane, wherever a data lives, right? And note that the radius basis function can be done in multiple dimensions, not just 2 and 3D. But the idea here is that we basically make these functions. They can be built off of each individual point, combined together to make one big function. And then that one big function can be projected downward into the lower dimensions to figure out where they split up on the original plane that the data lives on. Okay. So yeah, so again, why is this helpful? And I think this is where this will make a lot more sense, is that this is a 2D, oh, I did a 1D and 2D. This is a 2D to 3D. So this is the original data set here. And you can see there's no way to make a linear separable, you know, cut right here. But if you imagine like on this 2D part, you can make this in red, this kind of like mountain looking thing. That is the radial basis function. So the radial basis function will combine from all of these little points right here and basically create like this overall mountain. And so it's kind of cool is that you can actually imagine this, the way my analogy for like 2D to 3D is like, imagine it's sitting on a sheet and we're like pulling it up and we're basically feeling like, where do we pull up on the sheet? And we pull it up. So, you know, maybe these parts are pulled up more and these parts are like pulled down a little bit. And then you have someone else just come in with one scissors and just make a single cut. And essentially wherever that cut is, you know, you drop the piece of fabric or whatever you're pulling on, and you can imagine there's this nice, you know, non-linear cut. And essentially that's what we're doing here. So what's kind of cool is that we don't actually have to physically move these up and then find where the best way to split it. We can already predetermine where that RBF should be made. Okay. So again, this allows us to make it linear separable. And again, this applies for not just 2 dimensions, but higher dimensions too. Okay. So this comes down to like, well, how, you know, we kind of say, okay, we can kind of imagine, say, how much do you pull on each one of these points by how much kind of deal. And then they add them all together to make like one large, you know, like overall shape. One thing to kind of put in is this hyperparameter called gamma. And gamma, basically, the way I kind of describe gamma, is kind of like saying, sometimes people say like, oh, gamma is like higher parameter gamma. If you have a larger gamma, it'll be more narrow. Like, so you imagine like kind of like very like short, like little, like pulled up, or like you imagine like very small little circles instead of this big circle. And a small gamma, basically it's kind of like a more gentle thing. I like to think of gamma as like how hard you pull on the sheet. So if you imagine like if you had a very high gamma, you're pulling the each individual point where you're pulling up, you pull it up really, really hard and really high up. And so you're going to tend to overfit in that case, because essentially you're going to make these little tiny peaks. So what will happen instead of, if I had something like, let's say I had something that looked something like a small gamma might look kind of like what we see in this picture here, where like, you know, the separation is going to look like this. Okay. But if we had something like a very large gamma, like an extreme gamma, you might actually see things like this is the spots, this right here. So you'd have like these kind of like boundaries right here, because essentially you're pulling up on each part really extremely. So you'll see these boundaries be a lot smaller essentially. So, okay. Does that make sense? Some people like prefer thinking gamma like this. Some people like prefer thinking of gamma as kind of pulling up and stuff like this, but they're equivalent to each other. Okay. Makes sense? Any questions on this gamma in relation to the RBF? Okay. So I think this is where I think a little bit of code kind of is helpful to kind of see like how this works. So again, cool. Let me make sure it's the right one. So this is how to plot RBF. Okay, good. So this is actually from the support vector machine from sklearn. They talk about RBF. You see this full discussion. We're actually going to recreate this right here. So I'm just going to plot this out. I have the good old iris data. Again, this is just coming directly from sklearns. But basically, I'm just plotting this out. And so what we're going to do is we're going to adjust and adjust our C and adjust our gamma parameters for the support vector machines with an RBF. So essentially what we're going to see is like what happens when we increase C and what happens when we decrease C, what happens when we increase RBF or decrease gamma or increasing gamma. Okay. So if I run this guy now, and I'll kind of scroll up a little bit to kind of go, yes. So note that we don't really care about, oh, my thing can't minimize. We have this just part that's basically to help us plot things out and everything. But the main thing right here is going to be actually training it from here. So you can see in this case, we're doing something called a grid search, which we'll talk about in the future, but basically allows you to train out many, many parameters at once. But the main idea here is that we're training a support vector classifier, so SVC, okay? And basically we're just saying, all right, we're gonna try it with all these different parameters. In this case, a C range from minus e to the minus 2, or sorry, not e. It's called 10 to the minus 2, 10 to the power of 10, 10 to the power of 13. And then same thing for gamma, where we have 10 to the power of -9, 10 to the power of 3, and 10 to the power of 13. Okay, so we'll see like these extreme values. So, oh, did you not? Oh, I didn't call. No, if I just run it again, fine. Sorry, I didn't call matplotlib inline. There we go. Okay, so you can see this guy right here is that this is the same data set, and it's a little hard to see, but you can see a little bit. Maybe I zoom in a little bit. Okay. So you can kind of see this is the same, these are support vector machines, but they're changed with different hyperparameters. So see gamma here is like, 0.1. This is all gamma 0.1, this is gamma of 1, and this is gamma of 10, right? So 0.1, 1, and 10. And then you can see for C is going to be 0.001, 1.0, and then 100, okay? So you can see here at the very, let's kind of compare going from left to right here. So you can kind of see on gamma going forward is that gamma is very small. So we get very large kind of like these overall kind of like big orbs and stuff. And you can imagine if I do the analogy of pulling on this like fabric, it's like pulling it just barely. So it tends to kind of like just bulge up just a little bit. Versus as we increase gamma here, you can see those towers are essentially, those borders are going to be a lot, like a lot tinier, right? They're going to be a lot more narrow. And so it's like pulling up on even harder. And as we increase gamma to really, really high, you can see basically it's like pulling on each individual little data point. So you can see on the blue here, the boundaries basically are completely just encompassing just those individual points versus having something a little more, what's it called, like a little less overfitting. Does that make sense? Going from left to right here. Okay. And you can see on for C here, and I think C makes the most sense probably going in this direction, is that starting with C very, very small, right? So 0.001 all the way to something that's 100 here. What's happening is that we're caring more and more about the classification, or yeah, as we increase C, we should care more and more about the classification, right? So you can see here, basically it's thinking more about the boundary, but as we get into higher C, it doesn't actually do a good job, but you can actually see that it doesn't care about the boundary necessarily of this margin. It's just saying, hey, let me just try to get these points matched up. And so it's trying to make less mistakes. It's probably more obvious on the red by itself. You can kind of see it's kind of going through here. A little hard to tell. I think maybe, yeah, C's a little bit harder for us to kind of visualize, I think. But you can hopefully see a little bit that it's caring more about, it's basically making those boundaries a lot more varied, right? They're not having these nice smooth boundaries as we increase C. Does that make sense? Okay, yeah, so this is kind of like the overall, and you can see here, they also have this validation accuracy of saying, as we increase gamma down a very extreme level versus C, and seeing that this, I think yellow here is representing close to white is near 100% accuracy. So you can see that this is finding kind of like more or less the most optimal prediction part here. And note that there's, this in this case is 100 C, and this is like 0.001 gamma. You'd probably be closer to try to get something that's more moderate in this case. So probably like 1 and 0.1 for gamma. But note that just we can basically, as we kind of adjust each one, they kind of compensate for each other. Okay. Cool. All right. Any questions on how it's kind of play all together? Is that pretty good? Okay. Yeah, so support vector machines are really useful. They're really good for a lot of like medium sets. As you get into larger, larger number of like a large data set, it can start performing slower and slower. one suggestion I would say is that start off with a linear kernel to see how well it performs, and then see if you can, then the next probably best one would be like an RBF kernel. Also note that in sklearn, I wonder if I can find it real quick, but yeah, you can see SVC. So we have SVC, and then you can say a kernel can be either linear or RBF or polynomial. You see all these different ways you can create these different kernels and stuff like this. Note that if you try to do linear for this kernel, this is not as efficient as compared to using, let's see if I can find it real quick. Linear, oops, linear SV. So note that technically the support vector machine and using the kernel that's a linear kernel should perform in the same way as the calling linear SVC. However, linear SVC has some extra optimizations. So this actually tends to perform more efficiently than the traditional support vector machine with the linear kernel, at least for sklearn. But you can see the default is RBF because you can see that it does a pretty decent job of figuring out what the best, kind of, not the best, but like it's a little bit more flexible than the linear kernel where it essentially has to only make linear cuts versus like being able to kind of make these RBF functions. Okay. Cool. Yeah, so that's kind of all support vector machines with the kernel trick and everything. Any last overall thinking questions? Yeah. Okay. All right, I'll stop recording here.